Hey everyone. So today, we're diving into a paper that really gets at one of the biggest frustrations with AI right now. It's speed. We're going to ask why chatbots are so slow, and more importantly, we're going to explore a really radical new solution that could honestly change the entire game.
You know exactly what I'm talking about, right? You ask a chatbot a question and it just starts typing out the answer, piece by piece, almost like it's thinking out loud. Well, turns out that's not just for dramatic flair. There's a really deep technical reason for it, and it points to this massive speed limit that's just baked into almost every single large language model out there today.
So to get why they're so slow, first we got to talk about something called tokens. For an AI, language isn't really made of words. It's made of these things called tokens. Now, a token can be a whole word, like cat, or it can just be a piece of a word, like un or ing. Literally everything an AI reads and writes gets broken down into these little building blocks.
And the way that these AI models handle these tokens, well, that's at the very heart of their biggest limitation. It's the reason they're slow, it's why they're so expensive to run, and why they use up an incredible amount of energy. This right here is the bottleneck we're going to break down.
Okay, so here's the core of the problem. A normal AI model generates its response one single token at a time. It predicts the very first token, then it uses that token to predict the second one. Then it uses those first two to predict the third one, and on and on and on. You can see how this creates a huge traffic jam, right? It's a slow step-by-step process that just eats up massive amounts of computer power, which leads to huge costs and, yep, even some serious environmental concerns.
The way it works now is kind of like trying to have a conversation by speaking one single syllable at a time. It's just unbelievably inefficient. But what if, instead of that, an AI could learn to speak in complete words, or maybe even whole phrases, all in a single step? Now that is the breakthrough idea we're about to get into.
To solve this exact problem, a group of researchers have come up with a completely new way of doing things. It's called C.A.L.M, which stands for Continuous Autoregressive Language Models. And look, this isn't just some small tweak. This is a fundamental shift in how we think about making an AI generate language.
This brings us to the central question, the big what if. What if an AI could finally break out of that one token at a time prison? What if it could predict a whole chunk of text? Let's say 4 tokens all at once, in one single powerful step. I mean, that could make it generate text 4 times faster, right?
So here's how that actually looks in practice. A conventional model, it looks at all the text so far and just tries to guess the very next token. But C.A.L.M does something way smarter. It predicts what's called the next vector, which is basically a special compressed package that holds a whole group of tokens inside it. So by compressing, in this case, 4 tokens into just one of these vectors, C.A.L.M can cut down the number of steps it needs to take by a factor of 4. And that means, yeah, it could potentially generate text up to 4 times faster. We're talking about a fundamental leap in efficiency.
But here's the catch. Predicting a compressed vector instead of a simple little token is a much, much harder problem to solve. You can't just plug this new idea into an old AI model and call it a day. To get this to work, the researchers had to invent a whole new set of tools, basically from scratch.
The first tool they built is basically a super smart zip file for language. It's technically called an autoencoder, and it has 3 parts. First, you've got a zipper, or an encoder, that takes a chunk of, say, 4 tokens. Then it squishes them down into that single compact vector. That's the zipped file. And finally, you have an unzipper, or a decoder, that can perfectly reconstruct the original 4 tokens from that vector. And when I say perfectly, I mean with over 99.9% accuracy. It's an insanely efficient way to package up language.
But they hit a pretty big snag. Just creating this perfect little zip file, it wasn't enough. As the researchers themselves put it, the compressed version was exceptionally brittle. What that means is if the AI made even a tiny microscopic error when it was predicting the vector, the unzipper would just fail catastrophically and spit out complete nonsense. So the whole system had to be made a lot tougher, a lot more robust.
So, on top of building a much stronger zipper, they actually had to invent 3 other key tools. They came up with a new way to train the AI itself, a new ruler to make sure they could fairly measure its performance against the old models, and even a brand new dial to control its creativity. This wasn't just one new part. It was a complete end-to-end system.
All right, so they built this whole new toolkit. They put in all this work. But does this radical idea actually pan out? Let's take a look at the results and what this could really mean for the future of AI.
So the huge question, the one that matters most, is does it work? And the answer is a pretty resounding yes. The research shows that C.A.L.M delivers what's known as a superior performance compute trade-off. In simple terms, you get way more bang for your buck, more intelligence for less computational cost.
Now, inference flops is just a fancy way of measuring how much computer power it takes to run the model. And if you look here, a large traditional model, this transformer L, needs about 15 units of power. But the C.A.L.M XL model, it achieves pretty much the same performance using only 9.4 units. That is a massive gain in efficiency.
And this right here, this is the magic of the C.A.L.M approach. Because each step it takes is so much more powerful, you can actually build a model that's bigger, potentially making it smarter, while still having it run faster and cheaper than even a smaller traditional model. You really get the best of both worlds.
What this does is open up a totally new way to improve AI. For years, the main strategy has pretty much been just to build bigger and bigger and bigger models, a real brute force approach. But C.A.L.M gives us a whole new dimension to work with. We can make each predictive step more efficient, more meaningful. The paper calls this increasing the semantic bandwidth.
At the end of the day, this is a really big deal. This is not just some minor improvement. It's a potential paradigm shift in how we build AI, a move away from just brute force and a step toward a future of ultra-efficient, powerful, and way more accessible language models.
And that really leads us to the final question to think about. If the cost and the speed limits of AI were suddenly and dramatically lowered, making this incredible technology available to everyone, everywhere, almost instantly, what new applications, what new creative tools, what new worlds could we possibly build? That's the future that a breakthrough like C.A.L.M might just make possible.